In this video, I'm going to be showing you guys how to solve right Riemann sums, left Riemann sums, and midpoint Riemann sums. So the first problem that we're going to be solving using Riemann sums, or approximating some integral, is the x squared, the function x squared, from the values x equals 1 to x equals 5 in 4 subintervals. So we need to use 4 rectangles to solve the Riemann sum. Well, what is a Riemann sum? First thing we're going to do, we're going to draw our 4 rectangles, and we're going to start off with the right Riemann sum. So the right Riemann sum is a rectangle where the top right corner of the rectangle is the point that intersects with your graph. So if I were to draw another rectangle, it would look like this, where the top right corner is the one intersecting with the graph. And here is also another top right corner. And here's also another top right corner of a rectangle. So you might be wondering, what are these dotted lines here for? Well, we're trying to solve for the integral from x equals 1 to x equals 5. We're approximating the integral more specifically. And in order to do so, we need to separate each interval. We need to separate these intervals into 4 subintervals. So the big interval, the macro interval, is from 1 to 5, and we have 4 smaller intervals that we separate them into. And this just stands for the amount of rectangles that we're going to use for our Riemann sum. So we need to find the width of the rectangles in order to calculate the area that the rectangles hold, because we use the rectangles to approximate the area under the curve, correct? Well, in order to solve for the areas of the rectangles, we need their width and their height. Well, their height is given by the y value of each point, and the width is given by the spaces between these subintervals. So how do you calculate that? Well, for this one, it's very simple. The subintervals are just delta represented by delta x equals 1. So delta x just represents the subinterval length, or the width of the rectangles. But if you wanted a more analytical way to calculate it, you would subtract the largest x value, the rightmost x value, from the smallest x value, and then divide it by the amount of subintervals you want. And then you'll get delta x. And if 5 minus 1 is 4, 4 over 4 is just 1. So in this case, delta x is the width of our rectangles. And delta x is the distance between each subinterval. So that means this point here is x equals 2. If I drew that better, x equals 2. This point here, x equals 3. And this point is x equals 4. And the next point is x equals 5, which is the end of our interval. So first thing we need to do, we can draw a table to make this more convenient. Riemann sums are very inconvenient to solve for because they just require a lot of arithmetic, which can lead for a lot of room for error. But if you use a table, it helps a lot. So we're going to write down all the x values we need, which are 1 through 5. And we're going to write down the y values of each x value. So our function is just x squared. So the y values along this function are just x squared. So 1 squared is 1, 2 squared is 4, 3 squared is 9, and so on. So now that we have this table, we can either just use the table or we can use the drawing to help us. There's 2 options, and whatever you are, an analytical visual learner, I'll teach you guys, or I'll explain both along the way. So first things first, we're going to use the right Riemann sum. So think about the right Riemann sum is that we multiply the heights of the rectangles by the widths and add them all together, but we use the top right corner of our rectangle as the point that intersects with our graph. So the top right corner is at the x value 2. So that means the height of the rectangle is given by the y value at x equals 2. So the y value at x equals 2 is, let's put down right here. The y value at x equals 2 is 4. And we multiply 4 by the width, which is delta x, 1. We get 4 times 1. So next thing's next. We go to the next value, the next height. So the height of the rectangle is given by this point here. And this point is at x equals 3. So x equals 3 is given a y value of 9. Therefore, the height of the rectangle is 9. Again, we multiply by the width delta x, which is just 1. And then we keep doing this over and over. So this is 16. The height of this is 16 since it's at x equals 4. And then we just keep going. And once you add all these values together, you should get a approximated area of 54. Well, using the table, it's kind of easier than just looking back and forth between a graph. The table, all you need to do is just understand that x1 and 2 represent this first subinterval, and all you need to do is look at the y value of the subinterval that you are looking at. So this subinterval here has a y value at the right, x equals 2. So x equals 2 is at the right of the subinterval, therefore we look at the y value at x equals 2. So we start off with 4, and we just multiply the y values continuously until we hit the end by the delta x values. So we get here 4, and we move on times delta x, 9 times delta x, 16 times delta x, and 25 times delta x. So it's really just picking the right beginning number, and you just keep going on with the y values. Well, the thing about the left Riemann sum approximation is instead of starting off with the right subinterval, you start off with the left. So you multiply these 4 numbers with delta x in order to get the approximation. So we get 1 times delta x plus 4 times delta x plus 9 times delta x plus 16 times delta x. And if you add all these values together, you get 30. So the thing about the left Riemann sum is, let's actually draw it out. The thing about the left Riemann sum is that the corner of the rectangle that intersects with the graph is now the top left. So what we get here looks something like this, where the top left corner intersects with the graph. And as you can tell, this gives us an under approximation because we still haven't filled out this area and this area and this area and this area. So left Riemann sum in this case gives us a under approximation. A right Riemann sum actually gives us an over approximation since the rectangles actually go over the graph. Now, the thing about midpoint subintervals or midpoint Riemann sum approximations is that they're going to be a lot more annoying because you're going to be dealing with decimal numbers. Yikes. So the midpoint approximation Riemann sum uses the center, hence the name, uses the center of the rectangle as your height of the rectangle. The center of the rectangle is the point that intersects with the graph that you're going to be using to approximate. And it looks like this. So I drew the dots at the center of all the rectangles, and as you can tell, you have to draw another table for this. So if I drew another table, it looks something like this. And what I would need to do is find the x values between each subinterval. So instead of using the x values at the ends of the intervals like 1 and 2, I need to use the x values in the centers. And that will give me x values of x equals 1.5. This is 2.5, this is 3.5, and this is 4.5. Right? These are just numbers, these are decimal numbers in between the x values. So what I should do is draw the table and then write down the corresponding y values, because the y values will be the heights of the rectangles. Keep in mind, the thing about this is that delta x is still the same. Delta x is still 1, the distance between the points that we're trying to measure. 1.5 to 2.5, delta x 1. 2.5 to 3.5, delta x is 1. Their difference is still 1, so the distance between the points is still 1. But we have to use decimals now. This is going to be a lot more annoying, but we just need to calculate 1.5 squared, 2.25, 2.5 squared, 6.25, 3.5 squared, 12.25, 4.5 squared, 20.25. So now that we have all these values, we can use these to find the heights of your rectangles that you're trying to approximate with. Let's write down midpoint here. Since the y values are the heights of the rectangles and delta x is the width, we just simply need to multiply height times width plus height times width. And 2.5 is the height of this rectangle, and 6.25 is the height of this rectangle. Did I say 2.5? I meant 2.25. But if we add all these together, 12.25 times 1 plus 20.25 times 1, you should get a final approximation of 41. Now this is a better approximation than the right and left Riemann sums, But I mean, like, I guess in most cases midpoint will be a better approximation. But the best approximation is trapezoidal rule. That's a completely entirely separate video because of how. Okay, this is already kind of tedious. Trapezoidal rule will bring you to another level of I hate my life. So, you know, that's that, right? But this is how you calculate midpoint, right, and left Riemann sum. We'll do one more problem. Let's move on to that right now. All right, let's do one more. We're going to use right Riemann sum approximation and left Riemann sum approximation for this, with midpoint as well. Let's get the right and the left. So really, drawing out the graph takes so much longer. Literally, if you just use a table, it's going to be so damn easy. I'll focus more on the table for this problem, but I'll still do the visuals for you visual learners. But first things first, the right approximation. The right approximation, simply, again, the top right corner of your rectangle is what is going to be the point that intersects with your graph. So I can tell these rectangles get shorter and shorter, but again, you want to use the analytical method to find delta x for the rightmost x minus the leftmost x divided by the amount of subintervals you want. We want 4 in this case, so we get 4 divided by 4, which is just 1. That means delta x is equal to 1, therefore the width of the rectangles are equal to 1. So let's go ahead and get this straight. This is 1, x equals 1, equals 2, x equals 3. And we want to write down all the x values. So 0, 1, 2, 3, 4. Now if we just use square roots, you should get square root of 0. Square root of 1 is just 1. Square root of 2 is square root of 2. Square root of 3 is square root of 3. And then the square root of 4 is just 2. So using the picture, we can determine that the height of the rectangle is given by the y value at 1. The first rectangle at least, and the next rectangle is given by the y value at 2, next rectangle is given by the y value at 3, and so on. But instead, all we need to do is just skip the first guy, skip the first y value, and then just multiply the first y value, the second y value. Second y value is 1, multiply it by your subinterval length, which is delta x, which is 1, plus square root of 2 times 1, plus square root of 3 times 1 plus square root of 2. Sorry, not square root of 2. What am I saying? 2 times 1. If you add all these together, you're going to get some irrational number. You're going to get 3 plus square root of 2 plus square root of 3. I mean, let me put that in the calculator real quick. It's like some number that looks like 6.15. It's like approximating. It's like about. But, okay, how about for left Riemann sum? Well, for left Riemann sum, you're using the top left corner of the rectangle. Well, technically the height of the first rectangle is just 0. Right, it's just a straight line. So if I use the top left corner again, use the top left corner again, and then I use the top left corner again. So if I use the left, instead of skipping, just like the right, so the right Riemann sum approximation, I skip the first y value, instead we skip the last y value. So we just multiply 0 times delta x, which is 1, plus the next number, 1, times delta x, plus the next number, square root of 2, times 1, plus square root of 3 times 1. And the number I got off of putting this in the calculator is 4.15. So, kind of very under approximation. You kind of missed this entire chunk here of your integral or area. So, left, really big under approximation. Right, not that bad of an over approximation. But let's go ahead and do midpoint. So midpoint, again, is the more annoying one since you're dealing with decimal numbers this time. So if I were to set up the table, this is the x value, this is the y value. And remember, midpoint, you want to pick the, let's erase this. You want to use the center of the top of the rectangle as the point that intersects with your graph. So the center here looks something like this. Right? And the centers of each point are x equals 0.5. And this is x equals 1.5, right? And so on. So we get 1.5, 2.5, and 3.5 here. And the y values are given by some square root. I mean, like, if I just approximate, I'll just plug these into the calculator. This is 7.707. Square root of 1.5 is 1.22. Square root of 2.5 is 1.58, and the square root of 3.5 is 1.87. So using all these y values as they are the heights of the rectangles. With these y values, we can calculate the midpoint approximation. So first y value, 0.70 times delta x, which is just 1. Very simple numbers, delta x is just 1. The next y value is 1.22. Multiplied by delta x, we get the area of this rectangle next. Plus 1.58 times delta x. 1.58 is the height of this rectangle, and we multiply by delta x, which is the width of the rectangle, to get height times width, which is the area. And 1.87, the height of this rectangle multiplied by delta x, is 1. So if we multiply all these together, or add them all together, you should get a final approximation somewhere around the likes of 5.377. So this is the right approximation, left approximation, and midpoint approximation gives you somewhere kind of in the middle, not exactly, but then again, both of them, all of them are valid ways to find, approximate some area. And on a more important note when it comes to Riemann sums, the actual way, which is going to be my next the second video that I post after this, but the actual way to calculate Riemann sums is by infinitely decreasing the size of delta x. So we want to find the limit as delta x approaches 0. So when delta x approaches 0, you get smaller and smaller and smaller and thinner rectangles. And when the rectangles get so thin to the point where they basically just become lines, you could actually get an exact integral calculation of your, or at least exact area calculation of your integral. So instead of using approximations, you get an exact number by making delta x approach 0. That's just an important thing to note about Riemann sum, since this is a Riemann sum video. This is mostly just a practicing Riemann sum video. My conceptual explanations are all in the introduction to integrals. But, you know, I've been yapping for a while. These are nothing to do with the video. I guess I'm just talking to you guys at this point. But, as always, if you have any questions, put it down in the comment section. And if you found this video helpful, consider subscribing and liking the video. Thanks for watching.